Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Okay, so get this. Researchers just used nearly 7,000 top-tier GPUs, basically a chunk of one of the world's fastest supercomputers, to simulate a quantum chip.
A quantum chip that's barely bigger than your fingernail, mind you. And they did this to figure out how it might break before it's even built.
Wait, really? So the irony isn't lost on anyone, right? We're using brute force classical computing power to potentially fast-track the very technology that's supposed to challenge classical computing. That's wild.
Absolutely. It's a fundamental shift in how we approach building these incredibly complex machines. For years, the quantum computing hardware race has been defined by something the researchers call a build and break cycle, and it's exactly what it sounds like.
Yeah, I've heard that phrase tossed around. It sounds incredibly painful, both from an engineering and a budget perspective. What does that actually entail on the ground?
Imagine trying to build a super delicate, intricate clock, but you can only tell if it works after you've cast it in metal and soldered everything together. If there's a tiny flaw, you have to melt it down and start from scratch. That's essentially been the process for quantum chips. Qubits, the basic units of quantum information, are incredibly fragile. They're susceptible to environmental noise, things like thermal fluctuations or electromagnetic interference.
Right, so you design a chip, then you send it off to a specialized multi-million-dollar fabrication facility, right?
Exactly. And you wait weeks, maybe months, for it to come back. Then you put it in a dilution refrigerator, cool it down to near absolute zero, and meticulously test it. Inevitably, you find flaws. The report highlights a common one called crosstalk, where the signals meant for one qubit accidentally mess with its neighbors, or signal distortion, unwanted coupling.
So you finally get this thing, you test it, and it's got issues. Then what? You just start all over?
Pretty much. The entire process has to begin again. This build and break methodology, as the report describes it, is a huge economic bottleneck. Each iteration costs immense time and money, slowing down innovation significantly. It also creates a high barrier to entry because not many players can afford that kind of repeated investment.
And this has been the status quo because simulating these chips classically was just too hard.
Precisely. Previous attempts to simulate quantum chips on classical computers were severely limited. The sheer complexity of modeling the physics, down to the materials, the precise shape of components, how electromagnetic waves propagate in real time, was just too much.
So they had to simplify things, right?
Yes, they relied on what the report calls black box approximations. Think of it like this. Instead of understanding every gear and spring in that clock, you just know that if you turn this knob, the hands move. You abstract away the underlying physical structure. While these black box models are useful for understanding the logic of a quantum circuit, they can't capture the real-world physics that lead to chip failure. Issues like crosstalk are emergent properties of the physical layout and materials, and the black box models are blind to that.
So that gap between the idealized simulation and the physical reality is where most quantum chip designs would just fall apart?
Exactly. And that's what kept us stuck in this slow, expensive build and break cycle. Until now.
Okay, so let's get into what Berkeley Lab actually did here. How did they break this cycle? You mentioned 7,000 GPUs.
They essentially took a sledgehammer to the problem, but a very precise sledgehammer. Researchers from Berkeley Lab and UC Berkeley used nearly the full capacity of the Perlmutter supercomputer at the National Energy Research Scientific Computing Center, NERSC.
For a fingernail-sized chip? That just boggles my mind.
It does. This wasn't just any simulation. It was a sophisticated modeling effort that allowed them to simulate the chip with unprecedented physical detail. The report describes it as one of the most ambitious quantum projects ever run on Perlmutter.
So instead of abstracting things, they modeled everything?
Everything. They included all the physical details in their model, such as the materials used, the layout of the chip, and how components are wired and built.
So they're not just looking at the logic gates, they're looking at the actual electromagnetic waves propagating through the chip?
Precisely. They could see how control signals evolve and interact across the chip, revealing potential issues like signal distortion, coupling, and crosstalk with an unprecedented level of detail. It's like watching the actual electricity flow through every tiny pathway.
That's incredible. I mean,
They essentially took a sledgehammer to the problem, but a very precise sledgehammer. Researchers from Berkeley Lab and UC Berkeley used nearly the full capacity of the Perlmutter supercomputer at the National Energy Research Scientific Computing Center, NERSC.
for a fingernail-sized chip, that just boggles my mind.
It does. This wasn't just any simulation. It was a sophisticated modeling effort that allowed them to simulate the chip with unprecedented physical detail. The report describes it as one of the most ambitious quantum projects ever run on Perlmutter.
So instead of abstracting things, they modeled everything.
Everything. They included all the physical details in their model, such as the materials used, the layout of the chip, and how components are wired and built.
So they're not just looking at the logic gates, they're looking at the actual electromagnetic waves propagating through the chip.
Precisely. They could see how control signals evolve and interact across the chip, revealing potential issues like signal distortion, coupling, and crosstalk with an unprecedented level of detail. It's like watching the actual electricity flow through every tiny pathway.
That's incredible. I mean, the numbers must be insane for that level of detail.
They are mind-boggling. To model that tiny fingernail-sized chip, the simulation required immense computational resources to break it down into discrete grid cells and model its behavior over time.
And all that on 7,200 GPUs?
Yes, but here's the kicker. The payoff for this massive computational effort was a dramatic acceleration in the design process. They could run a complete simulation in a fraction of the time compared to the old methods.
That's a huge difference from weeks or months or even years of the old build and break cycle.
This is unprecedented. They could test multiple circuit configurations in a dramatically reduced time frame. Think about that. A full design iteration, from concept to fully simulated performance, in a fraction of the time it used to take.
Okay, so this is clearly a huge technical achievement. But what does it actually mean for the quantum industry? How does this shift from black box to glass box simulation change the game?
It's all about de-risking R&D. The core value of this high-fidelity simulation is the ability to accurately predict how a quantum chip will behave before it's even manufactured. Scientists can now spot potential flaws, like unwanted crosstalk or signal distortion, right there on a computer screen.
Instead of months later in a physical lab after spending millions.
Exactly. This approach saves immense amounts of time and money. It is a critical step forward to accelerate the design and development of quantum hardware. It dramatically increases the likelihood that the first physical version of a chip will actually work as intended.
So it's not just about finding flaws faster, it's about accelerating the entire feedback loop, right?
Absolutely. In the past, the feedback loop was painfully slow and often lossy. A chip was built, it failed, and designers had to try and infer why it failed from limited experimental data. Now, the process is much more precise and accelerated.
So you simulate the design, then you fabricate it, then test the physical chip, and then you compare the real-world data against the simulation. And any discrepancies help refine the simulation itself.
Bingo! It's a virtuous cycle. Not only does the initial design get better, but the simulation tool itself becomes more predictive with each iteration. It closes that gap between the digital twin and the physical reality, making future designs even more likely to succeed on the first try.
That's a huge advantage, especially when you think about the economics of this field. It sounds like this could really shake up the financial side of quantum R&D.
It absolutely could. The enormous cost of fabrication has been a major barrier, concentrating quantum hardware development within a small number of large corporations and well-funded startups. If a research group or a smaller startup can accurately test and iterate on its designs in a virtual environment, the need for constant, repeated access to those expensive fabrication facilities is significantly reduced.
So it lowers the barrier to entry?
Potentially, yes. A university lab, for example, could refine a novel qubit design through countless simulated iterations before committing the funds to fabricate a single physical prototype. This could democratize the race for better quantum chips, fostering a more diverse and competitive ecosystem. It shifts a significant portion of the R&D cost from physical materials and fab time to computational cycles, which, while not free, are becoming increasingly accessible.
So this is clearly a huge leap forward, but it's not like the quantum computer is suddenly here, right? This is an accelerator for the hardware development, but what's the ultimate goal that everyone's still chasing?
The ultimate goal for the entire field remains the creation of a fault-tolerant quantum computer. Right now, our qubits are highly susceptible to errors, limiting what they can do.
And fault tolerance means it can detect and correct those errors in real time.
Exactly. That's done through error correction, which requires significant overhead. It's a massive engineering challenge.
So, how does this Berkeley Lab simulation fit into the wider strategies of different quantum companies? Are there contrasting approaches out there?
Definitely. The quantum industry is pursuing various strategies. The report highlights two interesting ones. Take Alice and Bob, a startup based in Paris. They're tackling the error problem at the source with cat qubits.
Cat qubits, that sounds fascinating.
That's a hardcore hardware-first strategy.
And then you have companies like D-Wave, which seem to be on a completely different path.
They are. D-Wave focuses on a different approach, which has found practical, real-world applications today.
So how does the Berkeley Lab simulation relate to these different paths? Does it favor one over the other?
That's the beauty of it. It's modality agnostic. It's a tool that can be used to perfect the physical design of any superconducting quantum chip. Whether you're designing a specific type of qubit, an exotic cat qubit like Alice and Bob's, or components for D-Wave's approach, the fundamental challenge is the same: precisely controlling electromagnetic fields on a complex, multi-layered chip.
So the ability to simulate and eliminate physical-level problems like crosstalk is a universal benefit. It helps everyone.
Exactly. The report sums it up perfectly. The brute force classical simulation at Perlmutter doesn't pick a winner in the quantum race. It has the potential to make everyone's car run faster.
So let's tie this all together. What are the big takeaways from this Berkeley Lab experiment for our listeners? What should they really be thinking about?
First, the powerful irony. Classical supercomputers are now a critical tool for quantum advancement. The path to a quantum future isn't a zero-sum game. Brute force simulation is indispensable for solving the engineering problems.
And secondly, the economics. This model could really change the game for quantum R&D, lowering costs and potentially democratizing access.
Precisely. It shifts costs from physical fabrication to computational cycles, potentially opening the door for more players. Third, and critically, this is an accelerator, not a panacea. It doesn't solve qubit decoherence or invent new error correction codes. It's a powerful tool to tackle the complex engineering problems that are practical barriers.
So it's not a silver bullet, but it clears a lot of brush from the path.
A lot of brush, yes. And finally, it's a sobering reminder of quantum complexity. It took one of the world's most powerful supercomputers, using immense computational power, just to accurately model a single fingernail-sized chip. That underscores the immense challenge of not just designing, but actually building and controlling these incredibly sensitive devices at scale.
So, given all this, what do you think is the biggest lingering question for the quantum industry now that they have this powerful new tool? Are we just going to see an explosion of new chip designs, or will this highlight even more fundamental physics challenges?
I think the real question becomes, now that we can iterate so rapidly on the physical design, where will the next bottleneck emerge? Will it be in material science, the fundamental physics of new qubit types, or the sheer scale of integrating millions of qubits? The tool is there. Now the challenge shifts to how ingeniously we use it to push those boundaries.
That's all for Tech Disruptions. Thanks for listening. We'll see you next time.
Stay curious out there.